Now it's my great pleasure to introduce our keynote speaker for today, Professor Rick van den Ploeg from Oxford University. He is the research director in the Oxford Center for Analysis of Resource-Rich Economies, and formerly taught at Cambridge, the LSE, the European University Institute, Tilburg University, and the University of Amsterdam. He is also a former member of parliament and the state secretary in the Netherlands, and former vice chair of the UNESCO World Heritage Committee. Very, very long curriculum indeed. And not least from our perspective, he has a special interest in research in climate economics and natural resources. Today he will talk about pricing in transition and physical risk during the Great Transition. Rick, the floor is yours.
Thank you very much, Deputy Governor, for your interesting words and wise insights. I'm sure they will come back today and tomorrow in many of the sessions. And also thank you for your kind introduction, too kind introduction. So I'm going to, hopefully something will go, talk a bit about pricing in what I would call it physical risk and transition risks. I will take a slightly broader perspective. I mean, I know that all the sessions will go into the nitty-gritty of stress testing, where definitions matter. What is a green bond? What is a dirty bond? What is a green asset, more generally speaking? I'll take a more macro finance perspective, and also a little bit, think of me coming in from Nordhaus, the guy who got his Nobel Prize. Where are they there with climate modeling? What is lacking? Because 99% of the models that are being used don't really have a financial sector, don't really have asset prices, usually have only one sector of the economy. So they're pretty rubbish from the point of view of the stuff you're discussing today. So I'm going to come a bit towards you, but not all the way. So the stuff I will leave out, not because it's not possible, but just because it's already complicated enough, is I will not have credit constraints. So no Göttler, Karadi constraints. I won't have, and I won't have any networks, for example. And there's not even monetary policy in there. That doesn't matter, just to make the main points. If you want to do it, I have PhD students who have some papers on that as well, but I just decided to leave that out. Secondly, kind of mea culpa before I start, is that I focus on climate. But of course, sustainability is much broader than that. It's absolutely crucial to look at biodiversity. These have big potatoes effects. They have big effects also on the macroeconomy and the global economy. Half of me comes from a country which lives below the dikes, almost like Venice. And our biggest problem is water depletion because of too intensive agriculture, and nitrogen. So that basically we're killing all the green. And therefore it makes it impossible to build new houses or to build new factories. Belgium has the same problem. That's a sustainability issue. It is an issue of stranded assets. It is an issue of risk premiums. It is something you really have to worry about. So when we say climate, see it as a metaphor for biodiversity, nitrogen, water, and many other, and indeed also average. So that's what I want to say before I even start. So then I will talk about three things. I will briefly talk a little bit about physical risks. For me, physical risks are things like 99% of the models have it as a they take a bite out of gross GDP, world GDP. That's what people do, damages. I find that's not good enough. But you really need to think of it as disasters, which are like floods, storms, droughts. And then as global warming goes up, the intensities of these disasters, you well know in your stress testing, might go up by 1 degree Celsius. They may increase by a factor 5 to 8, depending on the type of disaster. So that's not small potatoes. These are big effects of global warming. So in contrast to Barrow-style disasters, which some of you might know from macroeconomics, these disasters increase with global warming. So more global warming. So if you want to think of it as a second externality. And then there's a third, these are kind of recurring disasters. And both the intensity of them occurring and the severity of these occurring will increase with global warming. I think that's much more important than the little bite taken out of GDP that's been measured by starting Richard Toll, later Bill Nordhaus, and all the integrated assessment models have that. And I think that's a too narrow view of the world. We really have to, and you are doing that. But when you do a lot of your stress testing, you look at those disasters and you see how robust are we to a lot of these disasters. Thirdly, which I think maybe you're not doing yet, it's extremely important, following the words of Timothy Lenton, and he's the kind of, if you want to learn about tipping points, the big guy is Tim, and he's in Exeter, but of course there are many others as well. And a lot of my work, and these are like irreversible shocks. So we're on the table, and suddenly you fall off the table, and you really go to a different system, and you've had an irreversible shock. So this could be like melting of the Greenland ice sheet, melting of the Antarctic ice sheet. It could be like the Siberian tundra. When that melts, all the methane comes out, which is much more aggressive than CO2, and it really accelerates global warming. Another one is we live in pleasant England or Holland, where we have nice temperate climate. If the Gulf Stream gets disturbed, which many people say will get disturbed as global warming goes up, then suddenly the temperate climates that we have in Europe, Northern Europe, will disappear. That will mean huge consequences for example, like the Netherlands and England, where my mother and father come from. but that's also seen as a tipping point, that there's a small probability that increases with temperature, so it becomes bigger and bigger with temperature, of an irreversible event like a tipping point. And then the question is, we know how to price in Nordhaus style disasters. Because if you just take out a part of GDP, it's just, well, what is the social cost of carbon? Does anybody know it? It's the present discounted value of all future damages, expected present discounted value of all future damages resulting from emitting 1 ton of emissions today. So those of you who've had finance, maybe Finance 101, know what the definition of a share is. It gets modified later on. It is the expected present discounted value of all future dividends. Yeah. So in a sense, this price of carbon, the social cost of carbon, is the same thing as a share price. It's the same thing as the price of a house. What is the price of the house? It's the expected present discounted value of all future imputed rents. And it's interesting that 99% of papers don't acknowledge that in the macro climate literature. But it's your turf. You know about asset prices, so you know about climate, and so you know about how to price carbon. But then the thing is, you need to price in that carbon. So it's a bit more than that. You don't need to just look at the fact that increasing global warming will take out a part of GDP because of loss in productivity. But you also need to price in a second and a third externality, namely the second externality being the idea that you increase the risk of recurring natural disasters. And the third externality, which is more complicated to price in, is to price in the risk of various tipping points. So I was going to show you some. So these are all physical risks, and I'll come about transition risks later. But basically, if you don't price in those physical risks, if you don't do, and I say pricing in, but pricing in is a metaphor for all policies, because all other policies depend on the price of carbon. If you don't have a good price of carbon, you don't have a lackluster, an unambitious climate policy. If you don't have an ambitious climate policy, if you don't price in all the physical risks, then you're storing up transition risk for later years. So it's the fact that people are not taking their actions, not doing their actions for dealing with physical risk, and then they're storing up, as people know it will happen at some point, because we signed up for Paris. It may not happen now, but it may happen in 2030, or 2035, or 2040. So you're building up regulatory risk, or if you want, transition risk. And I'll come to that in more detail in a second. So just to show you some pictures that you all know. So if the first picture you get out, if you look in Google and you're doing temperature and cumulative emissions, you see that 0 is the beginning of the Industrial Revolution. In my mum's town, Manchester. That's where it started. It started in all these cities we were close to coal. So the Industrial Revolution, we started burning coal. and then temperature went up. So all these models, these science models, show that the temperature goes up maybe to 4 or 5 degrees in the most extreme scenarios, and the black line shows that we now are closer to 1.5 degrees, if you want. I mean, almost we already overshot it, but on a trend a bit just below, if you want. But the point is, it's a fairly linear line. So most models, if you don't want to get too much into the atmospheric details of oceans and things like that, which I like to do, but that's physics, just for your purposes, you can think of it as temperature reacting more or less linearly to cumulative emissions. So cumulative emissions, you see the slope of that line is about 1.8 degrees Celsius per trillion tons of carbon. So so from that, for example, if it's a 2-degree cap or a 1.5 degree cap, you can just read off how much you're allowed to burn. So graphs like this are very important. So we use those all the time. And then a second thing to start off the chat. So I just grabbed, before I go into my own boring stuff, a recent paper from Nature by Kotzebue. I just took it because it's a recent one. It's indicative of the type of stuff you see. So and basically what I want to bring across is that the cost for mitigation, the green line, are very modest. So they are very modest, and of course these are different for any kind of model you do. But the cost of not mitigating, following Trump, if you want, are much higher. And of course, you see that if you go, this is shown across time rather than across temperature. You see then these mitigation costs for the different scenarios, and they are depending on whether they are 2.6 or 8.5. So 2.6 is ambitious climate policies. 8.5 is almost don't do anything, business as usual. And then of course, the less you do, the more business as usual. The huger these big damage costs come in, and they might kick in at 30, 40, 50% of GDP in the long run. So the first big message for all of us to our politicians, not to our central bankers. We don't want central bankers to have to clear up the mess that politicians have failed to solve. And that's another way of defining transition risk. It would never be the way you would define it, because central bankers are polite and are diplomatic. But that's the way I look at it. If politicians screw up, then the shit hits the fan in the financial system, and central bankers have to deal with it. So that's one way of thinking of it. It's a bit banal, but it's not such a bad way to think about it that way. So the first order lesson is to tell our politicians it's cheap. This is a lesson which was already mentioned by Nick Stern, Lord Stern, in the big Stern review. And it still stands today in most models. In my own models, it does. In various models, the main lesson, that main insight, forget about the numbers, is roughly right. So then you have to explain why pricing carbon is good. Most politicians don't like it. I've been in many rooms of ministers of finance, and they hate it. They say, no, they say pricing carbon is political harakiri. It's suicide. And I remember when I was in politics, I got called twice to my prime minister's office. For once, I was on the front newspapers to say this was in the early in the 90s, to say that we should price carbon. That my party went down in the polls, and then the second one was to tax the royal family, went down again. but so the idea is not a popular thing. So we have to think later about how to make it popular, how to get rid, to make sure that we don't get these transition risks, that they actually do something about it. And one of it is that it doesn't just cut demand, it also, without a price for carbon, you don't get green R&D. I invest in various small green companies, and they are just below break even. But if there were not these huge fossil fuel subsidies, but there were some green taxes, then a lot of green R&D would take off and green companies would take off. This is something that price incentive, which is so distorted at the moment, is not properly realized. These are first order of things we have to do something about. Without a price for carbon, you will not have any chance of having carbon capture and sequestration unless the government pays huge subsidies. Because what is carbon capture and sequestration? There is a price for carbon. You can make money if you put it away. So if you don't have a price for carbon, nobody's going to do it unless you bribe them to do it. So price for carbon is very important. Then so I could do this briefly because I said what I said in this section by words, but I will briefly show you a bit of a glance. I don't want to go into the technical details too much, but just to give you an idea. So these, again, don't look too much at those data. So there is these Nordhaus damages. They were about 9% of world GDP per degree Celsius. K stands for Kelvin, sorry, that's degrees Celsius. Yeah, I think of that. But now there's a recent paper by Diego and Kenzie. It came out last month in the NBR. And they use local projection methods to get impulse response functions. And they find that 0.9% goes up to 12%. It's the biggest figure. So they say, it goes, and then their cost of carbon, Northas got about 12 or 15. They get about $1,000 per ton of CO2. The best estimate for the cost of carbon, which corresponds to my own as well, is in a paper by Renner et al. In Science. And that Renner et al. Paper was on the instruction of President Biden to recalculate the social cost of carbon. And they take account also of all these various natural disaster risks, which are temperature dependent, and they come up about 200. So this 1,000 thing, which is it's basically the trick they do is they look at local temperature instead of global temperature, and then they pretend to get all these things, but it's just out fresh. But just to show you that if somebody says your cost of carbon is 15 or 50, don't believe it. It's at least 200, and it may be actually much higher. So then I have a second type of externality that I see these lambdas are just a probability that these natural disasters occur. For this illustration, I just showed them that I aggregate them, but of course in practice you'd have them for storms, for droughts, you have them for different natural disasters. And you see the increase in temperature, capital T. And the point of thing is, compared with barrel-style disasters, these disasters occur much more frequent, but the average loss you get, it is a stochastic distribution of the loss from a disaster, is rather less. So they occur more often, but they are less severe than the barrel-style disaster. Barrel-style disasters are typically like a Great Depression or a World War or a Ukrainian war or something like that. So they're much more prevalent, but they're pretty bad, but not as bad as the barrel shocks. And then the third one is what I would call a tipping point. And I just, for illustrative purposes, I just do a one-off tipping point. This is what Lenton likes as example, that suddenly the slope of that line I showed you is not 1.8 degrees Celsius between tons of carbon, but goes up to say 2.5. So the natural scientists say that's a good way, a reduced form way of modeling the tipping point. Well, anyway, be that as it may be, and then you have lots of other macro details that one bother you with, like risk aversion. The aversion to risk is typically bigger than your aversion to intertemporal fluctuations. That's something called Epstein-Zinn preferences. I will show you market-based preferences, market rate discount rates, and more what I would call ethical discount rates to make a huge difference. And then you get, I will go through this quickly, but the thing to, don't look at the formula, but typically you get these risk-free rates. They really get pushed downwards by climate uncertainty, by any form of uncertainty. And the reason for that is all you need to remember is precautionary saving. So if there's a lot of precaution, and you have precautionary saving for the normal, regular macro uncertainty, in the trade called geometric Brownian motion, is negligible. It doesn't mean very much. But the precautionary saving you do for climate shocks and for barrel shocks are very large. So that means if you do a lot of precautionary saving, that typically means in most of these macro finance models that the risk-free rate of interest is pushed downwards. So a lower risk-free rate interest is indicative of more precautionary saving. And then you see that the equity premium in these models is much higher than the normal equity premium you normally see, because you get the equity premium due to regular macro uncertainty. That's at gamma sigma square, where gamma is the risk aversion, sigma is macro volatility. But then you get a whole lot of terms due to these natural disasters. In the trade, it's called Poisson type uncertainty. And they are that summation sign in the last formula, that's really all the risk premiums coming in from these climate related risks. Okay. So and then all you need to see is there's a famous paper in Econometrica by Golosov et al. And they say that the cost of carbon is proportional to world GDP, and it's just that first term. It's a D1T. It's just like that, and it's proportional to chi. Chi is the slope of that curve of temperature versus cumulative emissions, and it's a present discounted value of damages. So you need to have somewhere some rate of interest. So that's just a classic formula. If you've done CAPM models, or if you've done a consumption-based CAPM model, it's the same formula. But the novel thing is that second term, that lambda 1TC times that term there, and that shows you have to price in an extra term. I already said it in words, and I want you to remember the words, not the formula, is that if the frequency of those natural disasters increases with temperature, you need to, it's a second externality, and you need to price it in. And that increases the price of carbon, becomes much higher as a consequence. The relevant rate of interest you need to use, it's just the risk-adjusted rate of interest, because these damages are proportional to GDP in almost all of these models. So therefore, in a future state of nature, when output is high, then damages are high too. So you have to take the risky rate of interest, not the safe rate of interest. So you can implement that. Then you can allow for climate tipping. So then there is an extra term. And again, do not look at the formula. There's an extra term to allow for the fact that as temperature goes up, there's a risk of climate tipping. And you need to price that in as well. That's a bit mathematical, a bit more of a monster, but we managed to get simple formulas out. And then we solve the whole model numerically overnight, sometimes 2 or 3 nights, but the simple formula gives you the correct answer within 0.1 percentage points. So to show you, these are the type of things you get. If the rate of interest is 5.3%, I think it's closer to 2%. So there's a large number of papers, admittedly, often in central banks. I won't mention which central banks. They use an R* close to 5.5%, a discount rate, which is very high. And that's because they take it from market-based preferences. But in my view, government should be much more far-sighted. This is a bit echoes the debate between Nick Stern and Bill Nordhaus. And then I would more agree to a rate of interest 2%. So if you look at the last row, that will be my preferred outcome. It will be something like the cost of carbon will be about $180 per ton of CO2. So that's it, because then you take account of the tipping point, you take account of the recurring disasters, and you get account of the normal Nordhaus damages. Notice that whether you used my little simple rule or whether you use grid-based optimization, these couple of nights running the computer, I don't care whether it's 179 or 81, it's pretty good. So this is the state of nature. Before I move to the transition risk, I should mention there's an alternative approach. Economists are not always listened to. Then you put in a cap of 1.5 or 2 degrees. It's very different. It's often called an efficient-based approach. But then you have to ask yourself, if you use a cap rather than these asset pricing formulas, what should the carbon price be then? Well, then typically you fix the tail. You say at the end, somewhere in 2050, we solve the issue. Then we know the cost of decarbonization. That's the carbon price. Then we roll back. What do we roll back? We assume it's like a hoteling rule. These firms want to be indifferent between pricing carbon tomorrow and being priced carbon today. So that means that the carbon price grows at the rate equal to the risk-adjusted rate of interest. So say about 3.5%, but it's not corrected for growth. So that's not the Nordhaus or Pigouvian approach. That's the cap approach. That's because economists have been quarreling too much. So in the end, the IPCC said, well, bugger you, we're going to take a pragmatic approach. Now the problem, why did politicians like this cap approach? You know, it rises the much steeper rate, and say for the UK, they even rise at 15%. I imagine that it's the case because I've been on, so you mentioned UNESCO. I know how political interference works. Politicians like hoteling paths. Why is it? Because you put less upfront and you do less front loading, you put it more in the future. Because if the carbon price can grow at say 3.5 or even 15%, like in some ridiculous studies, most of the action occurs later on. Politicians say great, because they're all in favor of doing it as long as the successors do it. But if you take a more economic-based approach, then it would grow, the carbon price would grow at the rate of growth of the economy, say 1.5 or 2%, and that will be much lower, and then you have more of the action upfront, which of course I'm in favor of. So I understand why the cap is there, but it carries the danger that more of it is shift into the future, so more transition risk. So then what can we do? So very quickly, we need a whole load of supplementary policies. I'm conscious of sitting opposite Patrick Bolton, and he's worked on various instruments, green new instruments for Africa and also elsewhere, and some of them will be discussed today. well, to be supplementary to carbon taxation. It's never just carbon taxation. It's also, there's a lot of learning by doing. These are immature technologies, green technologies. So you need to kind of subsidize them to get them to mature. You need green loans. You need in Europe, you need a border carbon tax to avoid carbon leakage. So there's a whole range of supplementary policy. I haven't got time to talk about it, but we know that they're important. But I want to just briefly, before I talk transition risk, make it more precise. And I added this because it's a keynote, so I wanted to be a bit more general. So I want to point out to you, why is it that the average carbon price in the world economy is $2 to $5 per ton of carbon, per ton of CO2? You can calculate that. There's a splendid database by the World Bank, and they give you all the carbon prices. Then if you take all the carbon prices, of course, they're high in Sweden and they're high in Europe, but the coverage is low. And secondly, many countries don't have any carbon prices. The average carbon price in Europe is, say, 2 to 5. It should be at least 200. So there's something wrong. Why? So my question is, and it's storing up transition risk. So why is it wrong? So the first thing to notice is that people are. We have in England, we have these sessions in the house of the Rothschilds between Oxford and London, and you get all these pinstripe suits come in, the bankers, and they all come in, and they all worry about stranded assets. But the thing is, before we go back one step, people are exploring and for new gas and oil and coal reserves like there's no tomorrow. So I mean, they still go. If you look at reserves, look at the BP data bank, they rise about 2% a year. It's just extraordinary. It should be going down, but no. And it's happily funded by hedge funds and pension funds and things like that. So we still, as a global society, we're facilitating with our pension funds. We're facilitating huge investments in those stuff. So they're called carbon bomb projects, and of course we are allowed, if you want to stay below our cap of 1.5 degrees Celsius. So this is 2 or 3 years old, but maybe burn at most 400 to 500 billion tons of CO2. But if we have reserves of 3.5 billion tons of CO2, so 3.5 trillion tons of CO2, we have 7 times as much. Every year I ask a student to go and look in the annual reports of all the big oil, coal, and gas companies and add up how much reserves they got and how much the implied CO2 in those reserves is. It's about a factor 7 times as high as we're allowed to burn. So then there's either two things. They either they either dodgy investments, and they probably have to pay, in contrast to what you think, they often have to pay high rates of return, because they're so dodgy, because they may fall flat. So they have to pay higher rates of return, these brown assets, because to compensate for transition risk. That if you go green, then they really go down. So they're going. Whilst the going is good, they pay you excess rates of return, but not after that. So there you see all the reserves, 400 or 500, that gray area. That's what you're allowed to do, but we have 3.5 trillion tons, 3.5 trillion tons of CO2, 7 times as much. That's not even counting the state companies like in Algeria or in Russia and things like that. If I add on to those, the factor will be much higher. This is measurable stuff. It's an underestimate. It doesn't count probabilistic stuff. So there's something really badly wrong in the world. The second thing, and I can be quick on this, is that it's all tipsy-turvy. IMF has calculated that, particularly the work of Ian Parry, that the world, we have about 6 to 7% of world GDP as fossil fuel subsidies. These are both explicit subsidies and implicit subsidies, because there may be exemptions and things like that. That's colossal. It's much, much larger to renewable energy subsidies. It's just the wrong way around. So you could argue we're not pricing carbon, we're subsidizing carbon. So what the hell is going on? No wonder you get, I mean, I'm not sympathetic to the tools of Extinction Rebellion, but you can understand why they go to the streets and many people go behind them. It's a bit like at home, you put the heating on and the air conditioning on at the same time. So you want to price carbon, but you're still subsidizing those fossil fuel barons. The third one is lesser known. How many of you have heard of the Energy Charter Treaty? One. So it's extraordinary. So this is a treaty which is completely orthogonal to Paris. So that means that basically gives all the legal rights to the fossil fuel companies and to the steel, cement, and aluminium companies, that if they have to go green, they can go to court and they find the law on their side and the government has to compensate them. It's completely ludicrous that countries are still subscribing to that. They should immediately get out of that contract as soon as possible. If they're in Paris, they should be out of ECT. And for example, for my own government, they only just decided to go out of it, but it hasn't quite happened. When you go out of it, there's always an overlap period. But it is really ridiculous. But you give all, and again, read this paper in Science by Tin Hara, and then you see it's really stopping green transition, because this is what makes governments hesitant to do what they should do, and this is what's building in transition risk. So that's another one. So another one, if you look at a politician, including myself, perhaps, we like to subsidize and we hate to tax, and we like to procrastinate things that are bad, that are unpopular. So that's what politicians are like. You can't blame them. That's what it is. But by delaying things, by introducing transition risk, the green transition becomes much more expensive. And really, I can give various studies, including my own study, not a factor 10 or 20%, factors more. And so it becomes, nobody worries about efficiency anymore, but we should, only the people in this room. But it becomes more, the longer you wait, it becomes more inefficient. Furthermore, I remember going to Algeria and I explained to the Minister of Finance this. He said, if they're going to change. So then what I've learned from your talk, Mr. Van der Ploeg, he said, I have to pump up the gas more quickly before all you lot go green. Well, you've understood the story, but then of course you realize that's very bad. That's called the green paradox. So that if you delay, you incentivize gas explorers and oil explorers to pump it up more quickly, and thereby you accelerate global warming, and you also increase transition risk. So it's also the cost of litigation goes up. I'd like to mention briefly, very briefly, because Patrick is here, but there's these two lovely papers by Patrick and Marcin Kakpacik in Journal of Finance. They're causing quite a bit of a stir because everybody is trying to re-estimate them with slightly different data and things like that. Some say it may not be true. My money is on them. And what they say, let me make it completely clear, is that if you have brown and green assets, I admit the definition is an issue, but in their case, the definition is clearly depends on how much emissions a company has, not emissions density, how much emissions a company has. That's, I think, is a good enough measure for how dirty you are. They look for scope 1, 2, and 3 emissions. That's pretty strong. They look at all 3 emissions. And my students have managed to replicate it on different data sets. And then they see, look, if you look, and then you correct for all the usual suspects. They're called the Farmer-French factors. And then they say, even when you correct for all the usual suspects, you get a couple of percentage points higher rate of return on these dirty assets. That's not because they're such good assets. That's for you to be indifferent between them and the green assets, because those brown assets are more subject to transition risk. If you look at banking detail, and I've seen more studies of that, not only the study I mentioned, various others as well, then banks have a tendency, correcting for all the usual suspects, to charge a higher rate of interest for projects that are dirty, and a lower rate of interest for projects that are green. There's another Journal of Finance paper. I'm not sure whether Patrick likes it, but it's a similar message by Su, Li, and Su. And they look at a broader range of pollutants, not just CO2, and they come up with a pollution premium of about 4.5% per year. 4.5% per year, it's not small potatoes, it's big stuff. It's not something you'd like to ignore. So this is, again, the brown assets getting on average a higher return than the green assets. Okay, so there you see the pictures that if you look at these things, it accumulates over time. The loads of other obstacles, you know them. The main one I want to mention here is you need to use the revenue. A lot of my work is about that. Don't do it the way Macron has done it. Then you get all the yellow vests. You need to use some of the revenue to compensate the losers. So you need to help poor people who don't have the money, they're either credit constrained or just don't have the money. Help them to get their roof insulated. Help them to get them a heat pump. Buy up their dirty cars and give them a subsidy for a green car. do whatever you need. And in some other countries, it may be better just to give income transfers to the poor people. If you don't do it, you get the populists coming in. You don't get a political majority. We often forget that, but this is most of my work is on that political stuff. That is absolutely crucial to reserve some of the carbon tax money or the money from the permits to get it politically across the line. But you must realize a Lexus is okay if you have a good salary, but if you want to buy an electrical car, you're poor, you're stuck. And they feel very unfair. They say, why you're hurting us? We don't even have the money to pay the bills. How can we afford to pay a roof installation? So unless you do something on that front, it's not being a social democrat or a socialist, although I am, but it just makes good sense. And the good news is, if you do it, you can increase welfare for everybody. Because if you don't do it, it doesn't get across the line, and then you get hit by all the damages. So it just makes good sense. Whether you're left wing or right wing, you have to do it. It's nothing to do with income distribution. It's having to do with trying to avoid those damages. One issue I won't talk about, but I could talk for hours about it, is that there are many behavioral biases. So one thing is, I want to honor Emmanuel Fary. I didn't know him that well, but a few times we talked only about theater and art, but he was one of the most brilliant economists, French economists I know of his generation. Well, probably of many generations. But he has this, one of his final papers was this thing on behavioral public finance. And then, so for example, then if you have a carbon tax, so in England, they say the temperature is 5 degrees tomorrow, but the skin temperature is -8. And what they mean is that there's a lot of wind and storm. It just feels much colder than it actually is. And I think it's the same. If you say the carbon tax is $100 or €100, then people feel maybe 200. It's very salient. It's very, so if you do that and you re-optimize everything, what do you get? Well, then you're going to over-subsidize green projects and you're going to under-tax carbon. You may even subsidize carbon. So these behavioral distortions help you to explain the terrible mess we're in. Anyway, so here's a big list of obstacles which are leading to transition risk. So let me now talk a bit about this transition risk. So I'm going to not talk about the things you talked about here. So I'm going to talk about, so what I want to give you is mechanisms in a model, two-sector macro model with asset pricing and optimal carbon pricing, where there is both physical risk and transition risk. Now, transition risk, I haven't talked about much, can be because we're not sure what the stance for climate policy is. Is there no climate policy? Is there a modest climate policy, or is there an ambitious climate policy? So, and say now I would say we have almost no climate policy. Might it jump up to more ambitious climate policy, or maybe even more ambitious climate policy? Similarly, for technology, is also a transition risk. So now we don't have a good technology for emissions technology. So imagine that, therefore, there's a probability that at some future you get a breakthrough. And then suddenly emissions technology becomes competitive. So I model these as, again, these +1 probabilities, and that these probabilities that you may go in there. So the interesting thing about transition risk, particularly the one about ostensive policy, is that in contrast to other tipping points, this is reversible. Because you can, you have Obama, you get Trump, you get Biden, and now we don't know what we get. But there's a lot of political stuff, and that political stuff causes a lot of disturbance, leading to a lot of premiums in asset prices, as I will show you in a second. So that's important. So we want to see what's the effect of this political uncertainty, of this transition risk, on green returns, brown returns, the carbon premium, and on the speed of the green stuff. So you could argue that if it's priced in properly, then brown gets more expensive and green gets lower returns and brown gets higher returns. So that should speed up the green transition. So in our macro model, maybe we see that. So I hope I can convince you of that. But then, so the fact that it's priced in is actually good, because it actually helps to move extra. It's even better not to cause transition risk and to do the proper thing, just to deal with the physical risk. But if you don't deal with the physical risk, it's some pricing in the financial markets which will help you along the green transition a bit. By far not enough. If you have transition risk, then in the end, everything is a lot worse off, but better than doing nothing. I'll show you. So I have ignore the model, but this is maybe you want to look at it. So I have three types of, the left column are three types of temperature responses, 1.8 degrees Celsius between touch carbon, 2.1 and 2.4 degrees Celsius. I have two states for the emissions technology, is it switch on or off? And then I have three states for climate policy. It's business as usual, be goofy is just modest, and the cap. And if you put a cap as well, it gets much more ambitious. So think of that as no climate policy, modest climate policy. And then there've been some studies which we take by more, and they calibrated those transition risks. So we just took that. So ignore that. For you to remember is that we have risk aversion, elasticity in terms of substitution. They need not be related to each other. We get the same kind of formulas. I ignore them, but they get extra interaction risk between climate tipping and transition risk. I don't have time to discuss those here, but they come out in the simulations. We calibrate the model, and we calibrate the model that we have a technology for net emissions based on a recent paper by Monetario et al. And we calibrate a political Markov chain based on a recent science paper. Of course, you could do anything else you want, but I'm just trying to give you the technology. The technology, therefore, you have your physical transition risks, and you have your two types of transition risks. So then we have an emissions intensity we fit as well. This is our, you believe, our calibration. So let me show you some simulation results to finish off with. And then hopefully you get some of the idea of it, to get a bit of the flavor. So the solid lines are the mean pass. So here I just show you the unconditional carbon tax. Well, we start with business as usual, and then as time goes on, you may flip into a state of modest climate policy or ambitious climate policy. So, but then the carbon tax goes up slowly. However, if you look at the conditional carbon taxes, that's conditional on having tipped to an active climate policy state. Then you start off with about $308 per ton of carbon. So when society starts pricing it, carbon taxes are quite large, but of course they depend on which part of the macro chain you are. So look at it now like this. So if you look at these policy states, so BAU is no policy, BGU is modest policy, and CAP is very ambitious climate policy. You see as time progresses, you get more and more dark gray, which is the modest climate policy, and eventually you get more and more active climate policy. And then you see, and in the climate tipping state, again, you see as time progresses, you are more likely to tip to the bad climate system. So that's the dark gray or the black one. The black one is really almost hothouse, global warming. And if you look at the technological state, again, as time progresses, there's a bigger chance that you move to the technology state. So these are based on other studies and things like that. Then if you look at the temperature range, they look a bit like in the bottom right panel. So you see the light gray area temperature stays below 1.8 degrees. There's a lot of paths where the area is between 1.8 and 2, and there's quite a few paths at the top where the black paths are bigger than 2.5 degrees Celsius. So look at these paths. So you look at the share of brown capital. So that starts very high, around 80–90%. And then and then you. I have how many more minutes left? I have 2 or 3 minutes, and then I'll be done. Okay, thank you. Then you see that although we have a lackluster policy because we start with business as usual, we're waiting for political systems to change and to become more political. Notice, by the way, within our calibration following that paper, our probabilities to move to the modest and ambitious climate state are endogenous. So they allow for the fact that they're a bit smaller when the share of brown capital is high because of the brown lobbies. And they allow for the fact that the probabilities are higher to move to an active climate policy state when the share of capital is green, because then you get more green lobbies. So there is a bit of thinking about that, which we talk about. Notice if you look at the net emissions path, that it goes negative. It can't go down more quickly because the technology is not available. All the results in the IPCC rely on negative emissions technology being available, but it's not available yet at a cost-effective way. So with us, it comes in a probabilistic way, and then you see that there's the average path, and the dashed paths are the 5 and 95% quintiles. There's also, in the left top panel, you see a dotted path, and that's the share of dirty energy. And you see the share of dirty energy slowly going down to completely green. Temperature, there are many temperature paths where temperature might go all the way up to 3 degrees, but on average, they go to about 2 degrees and maybe sometimes even lower. The reason why they looks quite good is because we allow for this negative emissions technology. And that's the path for output. So now let's look at the financial variables. So you see the top left-hand corner, you see the risk-free rate, the rate of interest on safe assets. And then you see that there are many paths where it goes very negative. Those are the paths that have, one, a high share of brown capital, and secondly, are very subject to transition risk. They're very close to a cap, or they're very close to this. The probability of having a transition to green policy is very high. And then there's going to get a lot of precautionary saving, and then you get those assets. And then you look at the bottom two graphs, you see not many people realize that these transition risks, you see that the 95% quintiles, it's asymmetric from the 5% quintile. So on average, there's the black line, but there are many paths for which there are high green risk premiums, but there are also very high brown risk premiums. So both paths price in that risk. So I get a lot of confusion. So the green thing, it should be negative green risk premium. No, it's actually positive. But the point is the brown risk premium is higher than the green risk premium. And therefore you get these carbon premiums up there. On average, maybe not so big, but in many paths, it can be very high to 2 or 3%, and sometimes even higher. So that's the story. Then I give you some sample paths, which I won't discuss, but I won't discuss it because of time. So now I want to finish briefly with saying, now let's allow for stranded financial assets. So the risk of stranded financial assets. So think about it. So most models that we have that are being used for policy purposes and for policy advice, they don't have irreversibility in investments. I think investments are really putty clay. I'm sorry, it's my Cambridge, UK background, but I think you invest, you can put them, when you invest, you can put them wherever you want. Once you've invested, you're pretty much stuck with it. But we have something in between. We have large amount of intersectoral adjustment cost. You can't really shift easily from a steel factory to a hospital because it takes a lot of money to do that. So if that's the case, if you don't have that, if you don't have irreversible, or you don't have these high adjustment costs, you will never get stranded assets. You need transition risk, and you need something like that the irreversible assets. There is also the whole issue of option pricing coming in, so that there is a transition risk. It will make you more hesitant to invest in green because you're not sure that it may go back again. So the main lesson, of course, for all these stories is governments change your constitution, tie yourself to a rule for the carbon price from now to 2100. It grows at 3.5% per year or 2% per year. Start at $200, but 200 euros per ton of CO2. Stick to it forever after, and then people know where they are, and then you get rid of all this hesitation or hold-up problems, that whatever you want to call it. So if you want to analyze this for the researchers here today, you would need to use models like developed by Avinash Dixit and Bob Pindak on real options to really get the grips on it. But you get it here in this model as well. And what we see is that the cost of stranding is sizable. The price of carbon actually rises. It becomes bigger than if you don't allow for stranding. And why is that? Because they have to try to avoid the stranding of financial assets, which is very costly. So they do a bit extra work to try to avoid it. So they put up the price of carbon a lot more, by about 20, 30% more, in order to lower that risk of stranded assets. And notice that the financial markets, I will show you in the graphs in a second, but they really price in the cost of stranding by having more precautionary saving, a higher premium for brown and green assets, and now the price of brown assets is, the carbon premiums are rather higher. So here you see it. Here you see the share of brown capital now goes completely down, and it goes to zero, and it stays there. And sometimes once you've gone there, it's difficult, you can't get back again. And here you see these carbon premiums, which are now rather higher than before.
And you see these are the paths I want to show. These are the percentage paths with financial stranded assets. There are about 15% of them. And the average stranded capital, it's about 15% of the paths that occurs. If I knock out the negative emissions technology, if I don't allow for negative emissions technology, the whole problem of stranded financial assets explodes. It becomes much bigger. The fact that you have negative emissions technology mitigates the cost of financial stranded assets. Now, I don't want to go in too much details about these numbers, but I think we need more studies like that. We have a general macro model with multiple sectors, intersectoral adjustment cost or irreversibility in assets, and then with physical risk and transition risk. If all you remember, that's what we need to have more work on, I think. And I think to make the link to stress testing, in the old days, stress testing was an Excel sheet. I'm sure that's not, I'm going to learn today and tomorrow, that's not the case. That you say, imagine that there's a risk. So remember after the financial crisis, there's a risk that house prices drop by 30%. How many banks will tumble over? And then you might have networks. Some of these studies we've seen in climate stress testing in the early days were a bit like that as well. So what I'm arguing is that stress testing should be done ideally also in a more endogenous framework, where you allow for changes in asset prices and changes in quantities and things like that. And I think academics are lagging behind. I've noticed in the last year, the last 2 or 3 years, not just Patrick, but the whole finance community is jumping on it. So whereas 5 years ago, nobody was working on it, it's become a very hot issue. So I expect a lot of good work on that. So I finish with this last slide. So we should think more of the models for transition risk. What are the mechanisms for that? Look a bit deeper into it. And negative emissions technology. And I want to leave you with the main thing to remember. If you don't deal with your physical risks, and there are many of them, and they're not just losing a bit of output. There are all these storms and hurricanes and droughts and floods. If you don't deal with these and you don't deal with tipping points, and you're just delaying that and waiting again, but that's politically convenient, then you're shifting the mess to the financial regulators and the central banks. You're creating more transition risk and more costly. And a final sentence, I have seen papers where people say, we should have a green Basel ratio or green interest rates or things like that, and then ask central banks to solve the problem of climate policy. I think that's a no-go. I think central banks, they should see stranded asset risk and all that stuff as a systemic risk. So they have a fiduciary duty to look after it. But you can't ask central banks to solve the climate problem. For that we need people, businesses, and particularly politicians. But of course, it's your duty as financial community to stand prepared when they screw up like so often. You have to be there with the dustbin and brush to avoid that the mess doesn't get as big as it could be. I thank you very much.